Now, before I take you to sigmoid, let me actually take you to the playground.TensorFlow, so you can see why you would use other activation functions. Let me tell you what we're looking at here. First, this is the neural network. This entire section. You have your features, your input dimensions, if we use TensorFlow terminology. Your hidden layers. Now, there is no hard rule or formula for choosing the number of hidden layers. But for most problems, 2 hidden layers is sufficient for most problems, or at least numerical problems. Data that is numerical, in like if you're doing regression. So for majority of the problems, this architecture is sufficient. For things like pictures and sound bites or text, no, you definitely need more elaborate neural network. And then you have your output layer. So this entire thing is your neural network. Then up here we have the hyperparameters. Remember, we said hyperparameters are synonymous with the configuration of the neural network. This will allow you to run this for a different number of epochs, so you can keep feeding your data to the network to see how it's doing. And then you have these hyperparameters, which allow you to control how the model learns and how to control the overfitting. So we can choose the learning rate, the regularization function, the regularization rate. And then here, to illustrate how effective a neural network is, they have chosen some very unusual shapes of data. I mean, look at this. Look at what's going on here. This is supposed to be like a scatter plot. We have 2 types of data, 2 data classes. The blue one is centered in the middle, and the second class is surrounding it. You're unlikely to see something like this in the real world. This is supposed to be like a extreme example. The point of this demonstration is to show you how a neural network is still able to classify the 2 classes in this data set. Here's another one. Here's another one. This is easier. And there's another one. Yeah, I mean, look at this. This is the point. Now, I have to play around with this, but we can use the same neural network to completely separate these observations. Now, how do we separate? We need to talk about regression for a moment. If I come back to this slide, if I go all the way to up here, this is supposed to be a picture that illustrates the application of the general regression model. Regression is used for modeling the direction of a data, and that's how you forecast. That's an application of forecasting, or as it's known as a regression. It's called regression because in a forecasting model, the observations should regress towards this line. A regression model, this is obviously not linear because, well, it's curved, can also be used to separate the data into 2 groups, if in the case of a binary classification. So this would be a polynomial model, and the idea is to draw the boundaries, or to draw boundary, or rather model the boundary of the data set. Of course, it won't be perfect, so I hope you can see it on my screen. We have some light green observations, some light green data points. In the second cluster, conversely, we have some of these dark green, or turquoise, if you like to call it, in the first cluster. But the majority are well partitioned. Now, here's another reason why you never want to use a linear model for classification. Because it's linear, it's a single line. You cannot use a single line to partition a sea of data points like the one you see here. Like imagine if this were a straight line. You could not clearly delineate this section. You can't also do this with a ReLU model either. Unless, of course, you use multiple ReLU models. Let me demonstrate. I'm going to return to the first example. I will not change the hyperparameters, and I will not change the neural network. I will not change the configuration. I'm going to hit play. And what I want you to look at is the animation in here. Now, what you're going to see is these epochs are quickly going to increment, like some sort of time lapse. And with each epoch, another thing you will see here is the loss. And we primarily care for the loss. We want this to converge to 0, and it will be animated here. So if I hit, let's watch what happens. Okay, so you want to watch this, and you want to watch this space over here. And we want to see if we're able to use 4 ReLU models, not linear, not polynomial. We want to see if we can use that ReLU, that L-looking model, 4 of them, to delineate the boundaries of these two classes. Ready? 1, 2, 3. All right, look at the loss function is already converging to 0. You see how it has climbed down? It is getting closer and closer to 0. We are not at how many epochs? 100, 200. I'm going to hit pause. 236 epochs. Watch what has happened. You see these boundaries? These are formed by those 4 ReLU functions. 1, 2, 3, 4. You can see here we have formed the first angle, and this is the second angle. Put these together, and you're able to, separate these two clusters of data. Is it clear? Like, has this example helped you understand what we're doing? What if I had set okay, and by the way, this is tanh. I should have changed this to ReLU. Let me set this to ReLU and try again. 1, 2, 3. I'm going to hit play. So you can see it still does a good job. Obviously, the corners are sharper, but that's what ReLU does. What if I were to set this to linear and hit play? It's not able to, because there's nothing linear about the pattern of this data. Let's try this other one. And I'm going to use ReLU again. And I'm going to hit play. And sometimes you actually have to restart this for it to work properly. So I'm going to hard refresh this. Try again. There we go. You can clearly see the ReLU right now. And for something like this, well, you need something that is more curved, like tanh. If I hit play, this might take a while longer. So the loss is it climbing? It's consistent. I think I'm gonna have to do a hard refresh to run this again. So tanh, can hit play once more. I remember this example always takes a bit longer, but it is ultimately able to, separate these two classes. Okay, look at the loss is dropping. It's getting closer and closer to 0 very slowly, but it is still not good enough. Let's let it run a little longer. It's 300. Is it going to go down to 200? Look at that. Look at that. Look at that. We're almost 1,000 epochs. And the test loss is kind of stuck at 300. So what we might have to do is play around with these hyperparameters, like change the regularization rate, maybe even adjust the batch size. But it's kind of, oh, look at that. Hold on. What? Something's happening. It's dropping again. Let's drop some more. That's 1,500 epochs. I don't know if I should keep running this, but it's done somewhat well. I mean, the test loss is still not good enough if we wanted to get closer to 0, but clearly we want to use this activation function. I think we'd hit pause here. But yes, had I played around with this, with the hyperparameters, I could have gotten it to perfectly, separate the two classes.